Good morning, everyone. My name is Pravin, and I'm a postdoctoral research associate at Texas A&M Transportation Institute. We're actually doing quite some work in machine learning and applied machine learning models, and this is one of them. Actually, this was submitted, I think, a year or so ago, so some of the things might have been that are present today could be outdated, but still the theory behind it is pretty solid. The title is long, but the presentation is not so. So this presentation is actually about it's an applied machine learning approach. So there was a bigger objective. We are actually developing a software for a DOT. It's a simplified Excel-based software. And one of the inputs for the software, we actually asked them to run a 28-day test and input those values, to which they came back and said, we don't want to do that. So the question was, how can we actually substitute the experimental work with a model? And this presentation would look at some of the approaches that we try to do that way. So overall, in terms of concrete durability and ASR, fly ash is most typically used SEM in United States, not only for ASR but also to achieve good durability performance in field. Now there are a couple of mechanisms by which this happens. There is soluble when you replace cement with fly ash, there is alkali dilution. There is also some overall contribution of alkalis from these SEMs, like such fly ash, Portland at consumption. There is also microstructure refinement, densifies concrete porosity, as well as the other parameters. But what is happening currently with the state of fly ash in US is there is continuously changing composition of fly ash. We have less and less of good quality and high reliable class F and class C traditional fly ashes, but we have a lot of new blended fly ash as well as the beneficiated ponded kind of varieties coming up. And this was, I think, one of the reasons why they asked us to do it, because running the tests every single time could be problematic. So again, going back to the previous slide, what is the focus of the presentation today is we are only looking at how does fly ash modify concrete pore solution, and how does machine learning help understand one of these parameters. If I just look at the theory of concrete pore solution, there are two parameters. One is total soluble alkali, and second is the alkali binding. The one on the left is actually the alkali coming in, and the binding is alkali being removed. So that is the net effect of the pore solution. Now this can be split into two parts. One is something that is coming down from the SEM, such as fly ash, at very early age, and the second is actually released as a function of degree of reaction. Now when we look at alkali binding, this is actually dominant based on the composition of the ingredient as well as the degree of reaction. So what happens in the left and the right is, as the reaction progresses, as the pozzolanic reaction happens, you have actually more alkali coming into the solution, but you also have some of the alkali going out because of the alkali binding. So these are two concurrent reactions that are happening. So just to give you an example, if we have a three-phase system with cement, fly ash, and silica fume, this is the typical values that you would expect. When it comes to dissolution of soluble alkali, cement, silica fume is much higher than fly ash and class C fly ash and class F fly ash. Whereas in terms of alkali binding, cement is the worst. Yeah. So these are the two effects. With some ingredients, if the soluble alkali dissolution increases, then the pore solution concentration also increases. If you have an ingredient which improves the alkali binding capacity, then the pore solution concentration decreases. For which for ASR mitigation, we recently developed a rapid screening tool for DOT, which relies only on early age soluble alkali measurements. And now we are actually going to replace this as well. But yeah, this is some of the work that we are doing here. Now this is the focus of this presentation, is we are developing a pore solution model where we can predict the long-term pore solution chemistry of concrete mixes, primarily to do with fly ash and silica fume in concrete. This is what we just saw, is the net pore solution chemistry is the net effect of soluble alkali and alkali binding. Now, if I just replace it with the equation, there is a numerator and denominator. The numerator just talks about alkali dissolution, which is soluble alkali, and the denominator is alkali binding. So what are the current approaches where this long-term pore solution composition or chemistry is actually determined? One, you always have an extraction method, but typically like it's usually reserved to the early ages, which is like 7 days. As cement paste or concrete ages, it's really difficult to extract solution. So not only we have a solution which is coming out as a function of pressure, but because of the pressure, the solubility of the ions also increases. So some of these extraction studies, you have a really high coefficient of variation. And that's the reason why we need a good model to actually predict this. So if I look at the current prediction models, there are 3 of them. From the accuracy to standpoint, like go from left to right. On the left side, the NIST model, which is the most simplest model. And then there was another model which was developed in 2019, which is called NIST. It's a better improvement over the traditional NIST model, and the third one is the GEMS thermodynamic model. The one on the right is extremely complex, but it's extremely reliable. We are trying to shoot somewhere in between, which is much reliable than the first 2, but it is actually less complex than the third one. So where it actually improves over the NIST, the second model was actually developed at our same institute like a couple of years ago, and what it actually does is it takes into the actual alkali coming out of the fly ash and measures it in form of available alkali, which is ASTM C311 test. But currently what is happening is there is a chance that this might be discontinued, and that's where DOT was not sure why they would want to do this test. There are a couple of reasons why this is being discontinued that I will present later, but it's like they understand the importance of this, but they also do not want to do this. So what is this available alkali test that we are talking about? Now, historically, like it was started back in 1940s by US Bureau of Reclamation. The test, when it was actually created, it was intended to measure the rate of alkali release from these pozzolans. So basically what we do is we take 5 grams of fly ash, mix it with 2.5 grams of calcium hydroxide or portlandite, put some water in it, and then cure it for 28 degrees at 38 degrees Celsius, and then finally extract and measure the alkali ion concentration in the water. But currently this is being withdrawn. There are like 2 specific problems with this. One is typically like this test has a high coefficient of variation. There's a poor agreement between different labs. And there's also some amount of research which says that the alkali release continues past 28 days. So the question is, why 28 days? But the major criticism of this test is coming that whatever this test measures, there's no correlation with the ASR expansion measurements. Now that is a valid criticism, but the whole intention of this test was never to correlate with the ASR. It was just to measure the amount of alkali coming out into the solution. And from that standpoint, this test is very, very important because we do not have a substitute of this test currently. There is no other test that actually measures the long-term alkali dissolution from any SCM into the pore solution, except for the extraction, which again, as I previously described, it's not only complex, but it's also pretty expensive. So that's when we started looking at this test in more detail, and we started like gathering more and more data, not just with regards to this test, but every other test out there that actually quantifies in any way the soluble alkali in concrete pore solution. So we had over 400 data points, both from literature as well as the experimental work that we did at TTI. The literature almost spanned 40 years, starting from 1980 to almost 2020, and it took into account different aspects of alkali dissolution, like how is the alkali coming out from fly ash? What is the reactivity? What is the mineralogy? And what is its effects on pore solution? We looked at different types of fly ashes here, class C, class F, blended fly ash, and some of them I did not put them here because the data was relatively low volume on that, which is remediated and harvested ashes. So when we actually put together all the data and look through it, what we actually notice is this is actually a pretty good test. Not if you want to compare it with the ASR, but if you just want to look at in terms of how much alkali does a typical fly ash would contribute into pore solution. Even without any information, you can just see from these charts that class C would contribute more than class F. And those are the kind of intels that we're trying to look through this data as we collect more and more. And if we take that one step forward, we can actually distinguish between 3 different fly ashes, like class F, class C, and blended ashes. A blended is actually a combination of both class F and class C ash, but you can have a distinct category even for that based on the data. Now typically, like if you want to predict available alkali, then there were attempts in the past where they used just silica and calcium contents of the fly ash to predict this. But when you go it a step further and try to understand why this test is so good, is every component that we don't see or we don't measure, this has a really beautiful correlation with some of them. Like if you just take the reactive phases, crystalline phases in fly ash and try to correlate, agreed the correlation is weak, but then there is correlation. And the most important is the second aspect, where each type of cement or like fly ash, silica fume would produce a different type of hydrated phase, like CSH. Cement usually has a very high C-bias ratio, which is around 1.7 to 2. Fly ash usually is around 1.5, and silica fume is really low, 0.9. But when you are taking this available alkali test and putting this perspective, you are getting a clear delineation on how to separate different fly ashes based on the C-bias ratio. And the third one is the most important, that there's in the glass, like how we measure the reactivity of the glass is we look at the parameter called non-bridging oxygen by tetrahedral. This test, the available alkali test, despite of all its criticisms, has really good correlation. The most important part is, although it's not a linear model, but these things we are able to distinguish between two different type of fly ashes, and that's what we were looking to get here. So what was the research approach? We first did the experimental study, and then we did a Bayesian machine learning model to predict available alkalis from different fly ashes. For that, I took about 230 data points of the 400 that I showed previously. And then the TTI model 2 was developed, and finally the validation study. Now very simply, like for this one, we used the Bayesian Monte Carlo Markov chain MC approach. And to put it very simply, what happens with the experimental stuff? Like if you are taking an equation AX plus BY equal to C. Now, if C is an output parameter which is coming from the experiment, it's never one data point. If I do an experiment to measure available alkali, there is a 9.7 coefficient of variation with that. Similarly, if I take just a fly ash and measure the ingredient composition, if I measure silica as 30%, there is a huge percent of variation, like between your lab, our lab, different labs. So what this approach really talks about is all these parameters are just not single points, but they are just distribution. If you have output data, that would be a part of huge distribution, which has a good mean and a standard different types of standard deviation. This distribution may or may not be normal, because when we are going for linear regression, we always assume it to be normal. But this approach does not consider it to be normal, and that's the beauty of this approach. So yeah, I mean, for this one, what we did is a three-phase approach, but what is important is the right part, where not only the literature data is scarce, it also has the question of reliability and complexity. Because when we are taking pore solution extraction measurements into consideration, as you go along with the age, the coefficient of variation is sometimes 15%. What do you do with that? Then also, like, if you want to take one single parameter, like as time increases on the graph below, the alkali actually in the pore solution increases, but after 28 days it decreases. So how do you actually analyze those cases? Well, the major findings from the machine learning model, because we use the Bayesian approach, is this. It's exactly what I was talking about, because this available alkali does not follow a normal distribution. And if you consider any normal model which is based on OLS, linear regression, that would typically assume it to be normally distributed. Similarly, like we only had one composition, which is silica, which was normally distributed. For everything else, it did not have a normal distribution. And so that's where like this Bayesian approach really helped. The results from the model was really good. We were able to predict with high accuracy not only the overall with the age, but also we were able to account for how it is released as a function of degree of reaction. And finally, what we did is, since we wanted a very implementable way, we actually developed the an equation out of it, where all of these parameters are just not single value points, but each of them follow a distribution based on all the historical data that we have. So what are the findings of the TTI model 2 overall? This is one example I can show you that is currently in works, and I think the publication is under progress, it's in the final stages. That we are now able to actually replicate some of the behavior, like if you see this particular one where you have fly ash, not only alkali dissolution increases with the age, but with the age the overall pore solution concentration also is decreasing. Overall, when we actually look at and compare it with the GEMS data, we are having some around 77 to 87% accuracy. Now here the question is, look, I have seen some models like when I attended other machine learning and AI where you can actually have much higher accuracy. Yes, it's definitely possible, or for us in this case, we are already dealing with a test that has low reliability. So some of the models to actually predict something like 90% R square, I would have questions in that. Now, when I compare it with the extraction measurements, these are compiled from the literature. The mean absolute error was around 7 to 11% overall. So how did we actually accomplish what we did? Is we actually made this model as a mix of empirical and kinetic model. Well, cement was kept constant, but machine learning was used to estimate soluble alkalis coming from fly ashes. And does the model have its sensitivity to PSC prediction? Yes. And it is also very sensitive to the composition as well as the mineralogy and reactivity of the fly ashes. Regarding its use and reliability, it's now a rapid estimating tool because we are now developing this as an Excel plugin. It definitely has a much higher reliability than any previous models, but of course when you compare it with GEMS, there's definitely some deviation there. Well, I would like to acknowledge the sponsors of this research, and I would also like to mention that I got a ACAE fellowship for this research in 2020, and thank you so much. If you have any questions, I'm here to answer.
Thank you very much. Very nice presentation. Questions?
All right, great presentation. Are they using it, and what's their feedback? I'm guessing it was for TxDOT, right?
Yes, it was for TxDOT, and we are going to hand them over in March next year. So right now, the feedback is that they really like what we have. They want us to extend it and measure the reliability on different types of fly ash, the blended ashes that are coming in the market, and that's why they find this model to be really useful. And well, they are actually looking forward to implement this. So yes, sir.
Can you take this model?
Yes.
And expand it to other types of pozzolans, such as like volcanic ash, trass stuff, and its effect?
And yes, that is one thing that we are definitely working on. So one of the key challenges we are facing in that regard is the amount of data that we have for fly ashes versus the natural pozzolans that we are working on. Because the mechanisms of the alkali dissolution from fly ashes are well understood, we were able to incorporate the physics plus data machine learning into one, as Stephanie was talking about, and achieve this kind of accuracy. When we are doing that for natural pozzolans right now and also for kaolins, clays, we are having challenges with the amount of data that is available out there. Second is each of these pozzolan may have a different mechanism of alkali's release as well as the alkali binding. But we are working through it, and we are positive that something we could have a good output maybe by next year.